Thank you for having me today. All right, so for the last decade or two, I think all of us in this room, if you are on the PFAS treatment side of things, we have been very focusing on treating greater and greater volume of the water and trying to achieve lower and lower criteria. So during that whole processes, if you are actually running the plant, you will know, you start to see that the media that you use will eventually spend. Then you start to watch the truckload, and truckload will spin media of the vessel, and the vessel of the media being hauled away. So at that moment, you know, basically your treatment technology didn't really destroy PFAS. So at that moment, I started thinking, maybe that is another mission we need to achieve, is really to chase the waste. And that waste chasing exercise is not just limiting to the spent media. You can refer to the sludge that if you manage in the wastewater treatment plants. If you can manage, you're talking about the gas, right, the off gas. And so there are a lot of waste stream being generated without destruction at all. So over time, the last decade or two, there are a lot of PFAS destruction technology involved. And pretty much you start thinking about those destruction technology are very focused on liquid waste, and which is a lot more easier to destroy. And with a very higher concentration and lower volume, you use the PFAS destruction technology to destroy PFAS in liquid. So I start thinking about, is that really the only pathway? That your piece of PFAS destruction can only focus on liquid waste. What if you have the solid waste? So that pretty much is the focus of my today's presentation. So what I will do today is I kind of walk you very quickly, just in case you are not on the PFAS treatment side of things. You probably want to know in what treatment process we can generate the latent waste. And part of it, I'm going to show you, if you actually use ion change resin or GAC to treat PFAS, at what point you need to do the change out, and likelihood how much PFAS is actually in your spent media. So once you start get that quantification in mind, you will realize how important that is. You want to see the end of the life where the PFAS will go. So I will also going to talk about, I'm not going to cover the liquid destruction technology today. There are a lot of vendors in this conference that you can talk to. So this presentation, I'm only focused on solid waste destruction, particularly for the spent media. And I do have one case study I want to share with you all, and I will quickly conclude with a summary. So I kind of break that PFAS removal technology into 5 different scenarios. The first 3 is probably the ones we're very familiar with, and the scenario 4 and 5, kind of like a new horizon. People start figuring things out. So the first one, the scenario is all we're familiar with, which is a GAC. Once the GAC spent, right, you kind of hold that GAC vessel back to the supplier likely, and then they were going to do some reactivation of the GAC. So the reactivated GAC will likely be resold to somewhere else, or there's an option for you is actually you take that reactivated GAC back to your facility and reuse. So there are some facilities that are doing that cycling thing. So basically, the GAC is reused, which really create the reuse advantage. The second option is also the media is being reused, is what we call regenerable ion change resin. That process is really, you use some kind of reagent, typically combining organic solvent like methanol as well as the brine solution. You wash the PFAS off the resin, and then you reuse that ion change resin over and over again. So there's one liquid waste that will be generated. It's called steel bottom. So that is a liquid waste. You can definitely take that steel bottom for destruction. The option 3 is very common because it's not all the GAC vendor has a reactivation facility. So they will recommend you to landfill the spent GAC. And single-use ion change resin is the same way. Very likely you spend single-use ion change resin, or the GAC will either end up at the landfill or incineration. So ideal scenario number 4 is Okay, whatever the single use and the GAC, those two technologies are very well proven. We know we can deal with it. You will treat the water to an extremely low MCL with no problem if you do that right. And so the number 4 option is what if you destroy PFAS and also destroy the media, meaning you make everything disappear. Nothing actually go to the landfill, nothing go to the incineration, you destroy PFAS together with the media. So that is the case study I'm going to show you later on. And the scenario number 5 is it's not that aggressive. It's more like I'm going to take that spam media, I'm going to destroy PFAS, and that spam media was not spam media, the media itself was not destroyed. And so that spam media will eventually, you can send that to the subtitle D, solid waste landfill. So those are the 5 scenarios I'm going to kind of quickly cover today. Before I talk about treatment technology, I want to quickly go over some of the real full-scale treatment system and have a sense in terms of how much of the cost we're talking about, comparing your annual cost of running a facility. So when you see the light blue and dark blue, is really to show you that dark blue is the cost for the routine operation, maintenance, and monitoring of a treatment system. And the light blue color is representing how much you spent on buying the media and also manage the spam media. So the buying the media and spam media, you add them together, can range from 0% to 60%. So that 0% is represent foam fractionation, because we just heard this morning about foam fractionation. The beauty about that foam fractionation is you do not buy solid media, right? You're only counting on air bubbles. So if you take that foam fractionation out, you generally speaking talking about 20% to 60% of annual spends actually contributing to buying the new media or manage your media. The management really vary, just like I said, you can choose to go to the incinerator, to the landfill, and depending on the distance, the transportation cost, depending on how frequently you change out. So that also gives you a lot of variation. So all this case study you show on this side of the full-scale operation system is not a pilot system, and they all show on this side are able to achieve the criteria. So the criteria really vary from full-scale facility to another facility, because some of the full-scale municipal facility decided to change out as soon as the moment they see any breakout, meaning any detection, they will switch, right? To the point that actually trying to meet the 70 parts per trillion or somewhere in the middle. So there are a lot of variation in terms of how the facility decided to change out. So the next thing I want to answer is how much actually is in your spam media. And actually, that is a much difficult task than I saw originally. Because as we know, 1633 is our go-to methodology to analyze PFAS in solid media. So what we did actually originally is like, we take the spam media, say ion change resin, and we run the 1633, and then we also collected monitoring data, because you do have a routine monitoring, even though it's not perfect, depending on the frequency of the monitoring, right? You kind of can get a sense, order of magnitude, how much of PFAS is being uptake by your spam media. So we realized 1633 only capture a very, very small fraction of the PFAS actually attached to the spam media. So at that point, we try to modify the 1633 using different solvents. We try to grind the media to see if we can enhance the extraction of PFAS out of media. That is very important. You start thinking about if you're trying to destroy PFAS in the spam media, you definitely need to know what is your initial concentration to start with. If that is so off, and your mass balance will never be right. So one thing we actually do here is we kind of enhance the methodology, which I'm going to introduce very quickly later on. And right here, just a general sense, say if you actually have a 20 tons of ion change resin in a vessel, we kind of estimated for each vessel, 20 tons, you will actually have 2 kilograms of total PFAS attached to basically absorbed by a vessel. So 2 kilograms of PFAS. So 2 kilograms of PFAS, every time, depending on how you handle it, how you manage it, it can be incinerated. It can go to the landfill. And remember, not all the spent media go to the subtitle C. Not all the spent media actually go to the hazardous waste incinerator. Your temperature may not rise when you do the incineration, and your landfill may leak. So that actually is a huge mass loading if you start thinking about your spent media. And how can you not to start thinking about managing your media in that way? So that really triggered in terms of how we're looking into how important to understand destruction technology to deal with the spent media. So this slide actually go over some of the technology that I can look into. So obviously, there's no intention to make this list very complete. So I realize there are a lot of technology vendors in this audience. If I miss any technology, please feel free to reach out to me and remind me there's some technology I need to look into. But on this table, you can see I list single-use ion change resin, GAC, regenerable ion change resin, and also regenerable GAC, right? There is a revived environment right now, start thinking about regeneration of the GAC using chemical solution, and they can combine with supercritical to destroy the regenerant. So the technology I'm going to quickly go through, including supercritical water oxidation, including gasification, ball milling, but it's not a normal ball milling. Actually, it's called piezoelectric catalyst technology. I'm going to go through very quickly, which is a non-thermal technology, and there's a gasification pyrolysis, but mainly gasification technology. In terms of if that goes through the regeneration process using chemical solution, then you have a liquid waste. I'm not going to cover the destruction technology for liquid waste today because there are way too many. Part of this table also tell you where they are in terms of stages of development, including the bench research type of development to the pilot study to full scale. And unfortunately, if you look at the full scale application, handling spent media is still limited to incineration as well as the landfill and also reactivation for sure. And in terms of a pilot scale, looking into the spent media, I'm including supercritical water oxidation here, but we are not quite there. But definitely there's some funding available to look into the supercritical water oxidation to destroy PFAS in the spent media. So I want to start with one technology, which is non-thermal, which is called piezoelectric ball milling. This is a very, very new publication. Just very recently in 2025, early this year, it has been published by a professor at Clarkson University, Dr. Yan. And he actually do a very small benchtop unit on ball milling, right? It's just you put a stainless ball and then put a high energy, they just mill it, right? So the spent media being milled that way. However, there's going to have no destruction at all if you're not adding what we call the piezoelectric matter, PEM, and he is using boron nitride and to combine with ball milling in order to break the PFAS carbon fluorine bonds. And so you can find on this slide, it actually achieved very good removal efficiency from the ion change resin that he used. He did 2 parts of the study. And the first part of the study is actually using the synthesize, meaning he spiked PFAS onto a fresh ion change resin and then do a defluorination study. So he was able to close the fluorine mass balance. He was able to demonstrate PFAS are completely defluorinated. He also used the spent media, the field-generated spent media. And in that study, he did not really focusing on close the mass balance. He only demonstrated that PFAS loss, which is removal efficiency. And I think everyone using DRE overstating about the treatment performance. Sometimes they only report removal efficiency, not the destruction and removal efficiency. So at least RE, removal efficiency, they achieve close to 100%. So very good. One problem is the PEM material, boron nitride. So boron nitride is not a cheap material. If you start thinking about 20 tons of the vessel I just mentioned, it will take you more than $2 million just to buy that chemical. And that chemical is not reusable, not recyclable. Basically, for each batch of the vessel you're dealing with, you have to spend $2.4 million right there. So right now, it's not economical, makes sense. However, he is trying to change a different kind of PEM or alternate a different ratio between the stainless steel balls and the boron nitride ratio. So more to come, but I appreciate someone looking into it because this is probably the only approach so far is not using the thermal technology. So gasification is one of the things under the bench scale study. I'm going to go through it very quickly. And then US EPA PITT, which is focusing on PFAS destruction technology, do the evaluation. And the first row right here mentioned about spent GAC and spent ion change resin. At that time, supercritical is not even available for evaluation. So now I'm going to start talking about the case study, which I think is very interesting. This is the Air Force Broad Agency Announcement Project. I'm the PI, and the project is managed by WSP, and technology provider is 370 Fort Water. And as I mentioned, the first thing I figured out, the challenge about this project is how do we actually quantify PFAS in the spent media? So most of the research right now is spiked with PFAS onto the fresh media, which is actually relatively easy to extract PFAS out. But if that is a spent media, it's very hard to say. So on this slide, if you can see, which I cannot really read very well, right here is basically you are talking about in some of the laboratory, they can only extract less than 0.1% of PFAS out of a spent media. And in some of the lab can actually extract 60% of the PFAS out of spent media. That is how wide of the range we're talking about 1633. So we generally feel like that is not doable. We need to find a different way to quantify PFAS. So what the first thing we do is we decided to try different solvents and combine the solvent, change to different solvents, and also do the cryo milling of the solid media. Cryo milling does help to increase the surface area for extraction. However, the final products of cryo milling is not uniform, meaning you have a very fine colloidal of particle. You also have a very large particles. If I take that large particle to do the 1633, the result sucks. You can see the lowest spot right there. Those are the cryo milled samples and go through 1633. But if I take that colloidal, very, very fine particle to run the 1633, the results are very close to estimated mass of a PFAS. So that is the first thing we learned. You need to do the right thing to quantify your feedstock. So the next thing we find is the client actually asks us to close the mass balance to do whatever we can. And we realize, again, if you're dealing with a solid media, using the extraction method is very challenging. So we actually take what we call direct CIC method, combustion IC method, which is not EPA method, it's not the STM, but we find it's very efficient and effective in terms of extracting PFAS out because it combusts the whole thing, the solid and the liquid, and converting into inorganic fluoride, and then we measure that inorganic fluoride. The challenge of that is the reporting limits is pretty high, so you have to deal with the source media with very high concentration. So scroll is a technology out there in the market for a very long time, and for the application of the PFAS destruction is relatively new. So it requires heating the temperature to about 374. You also need to apply high pressure. So we did a bench scale study. We completed. I don't have the pointer, but I hope you can see the feedstock right there look like milky. We actually have the spin ion resin in some kind of a suspended solution in order to make it injectable into this tiny, small treatment system. And the effluent on the right is definitely the liquid. And just a lot of people ask me how you talk about where is actually your spin ion change resin after the treatment. It's all gone, meaning the ion change resin is decomposed completely into CO2 and H2O. So that is what you see in the effluent. That is the only thing we got end of the treatment process. We do have a little bit of minerals, but very little, so little that it's difficult to quantify. And we also do some off-gas testing, and you can see the table to the right, and we've gone through all the target, non-target, top assay, TOF analysis, VOC analysis, SVOC, anion, cation, whatever you can imagine, NOx, SOx, all those gas detection as well. So what I'm trying to show you here, you probably it's very hard to read the scale, but the scale to the left, because we have the solid come into the system, liquid coming out from the treatment system. So we need to do the mass conversion. So the unit right here is nanogram per hour. So all of those are kind of like a flux unit. It's nanogram per hour. On the left-hand side, you can see 5 million nanogram per hour of the mass coming in. What is coming out is less than 100 nanogram per hour. So the treatment efficiency is awesome. And here's the table. You just simply will see all the nice. And we did 3 runs just to make sure our result can be repeatable over and over again. So we run the same condition for 3 times, and results are very similar. The only things we learn is the non-target analysis, the TOF, the non-target high-res MSMS is not very useful in terms of our DRE determination or our fluorine mass balance determination. And this is our fluorine mass balance, which is actually looking at the total fluorine inorganic, organic, in and out. So you can see the blue bar represents the mass coming in, the orange bar represents mass coming out. And we repeat 3 times, so you can see day 1 result, day 2 result, and day 3 result. We're pretty much close to the mass balance, surprisingly. So majority of the mass in the effluent is represented in the fluoride detection in our effluent. So this is our non-PFAS characterization. This is really something we really appreciate, because when you do a lot of destruction, people do not actually analyze the comprehensive list of parameters. So this is a very unique opportunity. We detect some non-PFAS related parameters to help us to understand if we actually degrade that ion change resin, what does that actually convert into? Because it's not GAC, just carbon, right? This is ion change resin. You have the chemical structure in there. So with no surprise that we actually detected some VOC and SVOC in our effluent, which is not expected. And those VOC and SVOC are mainly benzene, kind of BTAX compounds. So we were surprised a little bit. And there's another caveat is it actually generates very high concentration of chromium, which we don't really know where that chromium comes from. But it was not in the influent, but actually come out in the effluent. And good news is that you think about the complete destruction of our change resin, the purpose is to mineralize it. So the result actually show there's no detectable total suspended solids. It's all liquid, which is a great news. We achieve very high reduction of the TOC, and fluoride, once again, the concentration increased significantly. So because of the results, so the client did ask us to have a polishing treatment to address VOC, chromium, as well as residual PFAS. So this is my summary slide. With all I say right here, I try to say, yes, destruction technology is not ready to full-scale application, but let's think about a way to reduce the spam media as much as possible. If you can consider regenerable approach, consider regenerable approach. Use less. If you don't need the media, try not to use the media. And if you do have the media being generated really think about the life cycle, think about how you manage that waste coming out, have a good strategy to chase it, to manage it, to characterize it, mitigate it. Really just, it's not fair that we leave those problems to our next generation to address. So we should provide a solution today and have our next generation to kind of execute our solutions. So thank you.
All right, well, we have plenty of time for questions, so I hope you've been putting them down. I think we have a mic coming your way. We have a gentleman up here.